Good morning, student. Today we will discuss defect. Defect in a solid compound. So what is the definition of defect? So defect means irregularity in the arrangement of continuous particles in crystal lattice. That means if ideal arrangement is not there, and irregularity, otherwise radiation is produced, then it is known as defect. In each crystalline solid, always defect is present. Lowest temperature, when temperature decreases, then defect becomes minimum. Absolute zero temperature, there is no defect. But we know very well it is not possible to obtain the absolute zero temperature. That means always each crystalline solid contains defect depending upon their arrangement and based on temperature. Defect can be classified into two categories: point defect and second one is line defect. Definition of point defect: irregularity or deviation from ideal arrangement around the point or an atom in a crystalline solid. That means at particular point irregularity is produced. In case of line defect, irregularity or deviation from ideal arrangement in the entire row of crystal lattice. That means if totally in arrangement changes in the entire, here around only point deviation is observed. We have to study the point defect. That means further classification of point defect. Point defect can be classified into stoichiometric defect. Stoichiometric defect is also known as thermodynamic defect or intrinsic defect. Second, non-stoichiometric defect. Stoichiometric defect means it does not disturb the stoichiometry of the crystalline solid. Non-stoichiometric defect, that means it will disturb the stoichiometry. Again, third classification is impurity defect. Stoichiometric defect can be further classified into two types of substance. That means it is possible in two types of substance, in non-ionic solid and in ionic solid. When it is present in non-ionic solid, they are classified into vacancy defect and interstitial effect. When it is present in ionic solid, then they are classified as Schottky defect, and second one is Frankel defect. Frankel defect is also known as dislocation defect. Now, non-stoichiometric defect. Non-stoichiometric defect can be classified into two categories: metal excess defect and metal deficiency defect. Metal excess defect further can be classified into two categories: metal excess defect due to anion vacancy, and the second one is due to extra cation at interstitial site. So these are the classification of point defect. Now we will discuss each defect in detail. So starting from stoichiometric defect. So stoichiometric defect are present in non-ionic solid and ionic solid. Again remember, stoichiometric defect means it does not disturb the stoichiometry of the compound. When it is present in non-ionic solid, then it is classified into vacancy defect and interstitial defect. Vacancy defect means what? Suppose these are the arrangement of constituent particles. Vacancy defect means some of the particles are absent. That means their place are vacant, like this. Suppose these particles are absent. That means this place is vacant. Suppose these particles is absent. Then this place becomes vacant. This is known as vacancy effect. That means some of the particles are missing, otherwise they are absent from their position. What will be the effect due to vacancy defect? So these places are become vacant, particles are absent. That means density. Density. What will be the effect on density of the substance? So obviously, volume remains same, particles are absent. That means density decreases. Now, how the vacancy defect can be produced? So simple. When heating is carried out, generally heating is carried out, then vacancy defect will be produced. Now, second one is interstitial defect. These are the arrangement of constituent particles. Interstitial defect. Interstitial defect, that means constituent particles are sit in an interstitial site. That means suppose these particles is shifted here. And here position becomes vacant. That means some of the particles move in interstitial site and their original position becomes vacant. So this is known as the interstitial defect. This is known as interstitial defect. Now we are thinking here, that means mass at particular position increases, but all over mass remains same. That means density remains constant. But suppose we are adding another substance, that means extra substance. Extra substances are present at interstitial site. Then density increases. That means as per NCERT textbook, here given density increases. But if we are adding foreign substance, extra substance, and they occupy interstitial site, then density increases. So this is interstitial defect. Now, when these defects are present in ionic solid, then they are classified into two categories: Schottky defect and second one is Frankel defect. So actually, Schottky defect is basically vacancy defect. So we are studying here Schottky defect and Frankel defect. So remember, Schottky defect is basically vacancy defect. It is basically vacancy defect. Vacancy defect found in ionic solid. And Frankel defect is interstitial defect basically, and found in ionic solid. So remember here interstitial defect. Now how the Schottky defect are produced? So Schottky defect is basically vacancy defect found in ionic solid. Ion in solid means positive and negative ions are present. Now, vacancy defect means this type. That means here positive and negative ions are missing. That means some of the positive and negative ions are missing and their position are vacant. Suppose here positive ion this is missing, then compulsory one negative ion is also missing. Reason to maintain the electrical neutrality. That means equal numbers of positive and negative ions are missing. Equal numbers of positive and negative ions are missing. Reason to maintain the electrical neutrality. Now, in case of Frankel defect, so Frankel defect also present in ionic solid. That means here positive, negative, positive, negative, positive, negative. Negative, positive, negative, positive, negative, positive, positive, negative, negative, like this diagram. Frankel defect is basically interstitial defect. That means here ions shift towards the interstitial side. So we know very well positive and negative ion. The positive ion having smaller size compared to negative ion. That means here positive ion shift in interstitial side. That means here positive ion. And here its original place becomes vacant. That means when positive ion, that means cation shift in interstitial side. Interstitial defect, that means Frankel defect is produced, and its original position becomes vacant. That means it creates vacancy defect on its original position. Cation shift in interstitial side, therefore it is also known as dislocation defect. That means here cation moves in interstitial side. That means Frankel defect is basically interstitial defect, Schottky defect is basically vacancy defect. Now discussing Schottky defect. So Schottky defect, equal numbers of positive and negative ions are missing. In which type of solid compound Schottky defect are produced? So generally 1 and 2 points remember. Positive and negative ions having same size. Same size. Again coordination number. So coordination number is high, generally 8 or 6. In situation, Schottky defect are produced. Schottky defect are found in alkali halide. Alkali halide. That means NaCl, KCl, okay, so on. What will be the effect on density due to Schottky defect? Equal numbers of positive and negative ions are absent. That means obviously this one type of vacancy defect. So density decreases. Density decreases. Now always positive and negative ion equal numbers are missing. That means this defect is found in always in pair. That means in even numbers. That means we can say always Schottky pair is present. Pair defect. And the numbers of Schottky defect are significant. Say example, in NaCl crystal at the room temperature, in 1 centimeter cube, 10 power 6 Schottky defect are present. 10 power 6 Schottky defect. In 1 centimeter cube, approximate 10 power 22 ions are present. That means we can say one Schottky pair defect is present. One Schottky defect pair is present for 10 power, because total 10 power 22 ions and 10 power 6 Schottky pair is there. That means one Schottky defect pair is present for 10 power 16 ions. Now, in case of Frankel defect, we know interstitial effect. Cation moves in interstitial site. That means interstitial effect is produced and its original place, vacancy defect is produced. Now, what will be the effect? So, effect is on density. So, only cation moves in interstitial site, mass remains same. So, density remains same. That means no change. No change in density. Second, in which type of compound Frankel defect is produced? So 1 and 2. In case of Schottky defect, same size. Here, large difference. When there is a large difference in positive and negative ion, large difference in size of positive and negative ion. Second, here coordination number is high. So here coordination number is low. Generally 4 or sometimes 6. In which type of compound it is found? So generally halide of silver. That means it is found in AgCl, AgBr, AgI, JNS. Okay. In all cases, positive ion moves in interstitial site. That means here Ag plus. And in JNS, Zn plus 2 ion moves in interstitial site. Now remember, in AgBr, that means silver bromide, both defects are present, Schottky defect and Frankel defect. Both defects are present, remember, in silver bromide. Now, here it is completed Schottky defect, Frankel defect. Now we are discussing impurity defect. Impurity defect here. Impurity defect. Impurity defect means we have to add certain foreign substances. That means it is called impurity from outside. Taking the example of NaCl. Suppose molten NaCl is there and in which SrCl2 is added and crystallization is carried out. In molten NaCl, SrCl2 is added and crystallization is carried out. Then what happens? We know very well Na plus Cl minus, Na plus Cl minus, Cl minus, Na plus Cl minus Na plus. Again Na plus Cl minus Na plus Cl minus Cl minus Na plus Cl minus Na. For the simplicity purpose, Na plus and Cl minus are arranged like this. And when crystallization is carried out by adding SrCl2, then what happens? Here positive ion is Na plus. In case of SrCl2, positive ion is Sr plus 2. That means positive charge here plus 1, here plus 2. That means when crystallization is carried out, to make the electrical neutrality, one Sr plus 2 replace to Na plus to balance the charge. That means one Sr plus 2, when Sr plus 2 enter, here Na plus is removed, again Na plus is removed, when one Sr plus 2 is added. One position is occupied by Sr plus 2 and second remains empty because one Sr plus 2 replaced to Na plus. That means here vacancy defect is produced. This place becomes vacant by addition of SrCl. Therefore, it is known as impurity defect. Numbers of vacancy defect. Numbers of vacancy defect, otherwise numbers of vacant site, is equal to the numbers of Sr plus 2 added. Numbers of Sr plus 2 added. Similar example is done AgCl. During crystallization of AgCl, when CdCl2 is added, one Cd plus 2 replace 2 Ag plus. That means here also numbers of vacant site produced is equal to the numbers of Cd plus 2 ions added. Now we are discussing non-stoichiometric defect. Stoichiometric defects are completed. We are discussing non-stoichiometric defect. Non-stoichiometric defect means it disturbs the stoichiometry of the compound. That means stoichiometry will be changed. Non-stoichiometric defect having two types, metal excess and metal deficiency. We know very well. Metal excess defect having two types, due to anion vacancy and due to presence of extra cation at interstitial site. So first we are discussing due to anion vacancy. Taking the example of NaCl. NaCl crystal, when heating is carried out in presence of sodium vapor atmosphere, what happens? This is Na plus Cl minus, Na plus Cl minus, Na plus Cl minus, Cl minus, Na plus Cl minus, Na plus Cl minus, Na plus. Here also Na plus Cl minus, Na plus Cl minus, Na plus Cl minus. For the simplicity purpose, structure of NaCl crystal in which positive and negative ions are added. NaCl crystal is heated in atmosphere of sodium vapor. Then what happens? Sodium vapor will be deposited on the surface of NaCl crystal. Now, when sodium vapor is deposited on the surface of NaCl crystal, then this Cl minus, one of the Cl minus diffuse towards the surface. Here sodium metal is there, here Cl minus. So to form NaCl, this sodium atom remove the electron and convert into Na plus and Cl minus. Now this Na plus So Na plus electron. That means this sodium is converted to Na plus electron, release electron. These Na plus and Cl minus are present at surface. Now this position becomes vacant. Position of Cl minus. Now Cl minus having negative charge. That means due to anion vacancy. That means anion means negative ion. Position of the negative ion becomes vacant. Now this electron, when Na is converted to Na plus electron, this electron occupies the position. Due to anion vacancy, that means this position is vacant. This electron moves here. And this electron is responsible for the color of NaCl. This is known as F center. F center. Harbingen center, that means color producing center. Color producing. That means when visible light falls on this, electron will absorb energy, becomes excited, go to higher energy level, again come into original position, and extra energy will be emitted in the form of radiation, and corresponding to the wavelength of the radiation, color will be observed. So in case of NaCl, we observe yellow color. Similarly, in case of LiCl, when LiCl crystal is heated in the vapor of lithium, then it is pink color. Similarly, KCl, violet color is also. Metal excess, that means we are heating the crystal of alkali halide in metal vapor atmosphere. That means metal amount increases and color produced. Reason for the color is this electron, otherwise it is known as F center. Now second is due to presence of extra cation at interstitial site. A simple example is that Zn crystal is white color, but when heating is carried out, it becomes yellow. That means Zn heating is carried out, Zn plus 2 plus 1 by 2 O2 plus Bn. This oxygen gets removed. Now this Zn plus 2. This Zn plus 2 produced when heating is carried out. This Zn plus 2 occupies the interstitial site, presence of extra cation. That means when heating is carried out, extra cation Zn plus 2 is produced, which occupies the interstitial site. And this electron occupies the position near the interstitial site of Zn plus 2. And this electron is responsible for the color. That means when heating is carried out, Zn turns to yellow. The reason is this electron. Amount of Zn plus 2 increases. That means we can write formula Zn 1 plus Xo. It can be also revised like this. Now, metal deficiency defect. Here metal excess. Amount of metal increases. Here amount of metal decreases. Metal deficiency. That means in some solid, amount of metal is present less than the requirement. That means as per stoichiometry, this is the requirement, and amount of metal is present compared to less than the calculation from stoichiometry. Say example FeO. Actually, oxygen having -2 charge, Fe having +2 charge. So this is as per stoichiometry compound. Proportion is 1:1. but actually FeO does not exist as a FeO, but proportion of Fe is less. Reason, Fe is present in the form of Fe plus 2, O minus 2 to Fe plus 2. Now some of the Fe plus 2 are missing. Some of the Fe plus 2 are missing. And charge is balanced by Fe plus 3. Charge is balanced by Fe plus 3. Here charge is plus 2, here plus 3. That means suppose Fe plus 2, Fe plus 2, Fe plus 2. Here balancing charge 3 Fe plus 2 equal to 2 Fe plus 3. When we are balancing charge, Fe plus 2, Fe plus 2 and Fe plus 2. Now some of the Fe plus 2 are replaced by Fe plus 2. Now we are maintaining charge. Then 3 Fe plus 2 having charge equal to 2 Fe plus 2. That means when replaced, okay, these 3 Fe plus 2 are replaced by 2 Fe plus 3. That means Fe plus 3, Fe plus 3. That means one position becomes vacant. That means proportion of Fe plus 2 is less. Reason, 3 Fe plus 2 balanced by 2 Fe plus 3. That means here 3 Fe plus 2, but when replaced then only 2 Fe plus 2 is required. That means FeO compound does not exist as a FeO, but proportion of Fe is less. That means it is generally present at the 0.93 to 0.98. That means proportion is less. Proportion of Fe is less than the stoichiometry. We can calculate how many percentage of Fe plus 2 is present in Fe plus 3. Reason, this is base proportion Fe. That means some of the Fe plus 2 are replaced by Fe plus 3. So we can calculate. This is known as metal efficiency. So how to calculate percentage? So simple one example is here. Calculate percentage of Fe plus 2 and Fe plus 3 in Fe 0.980. Now proportion of Fe is less compared to stoichiometry. That means Fe plus 2 and Fe plus 3 both are present. So simple. Assuming oxygen atoms are 100, then automatically Fe atom equal to 98. Now these 98 atoms are available in the form of Fe plus 2 and Fe plus 3. That means Fe 98 atom. Some of them are exist at Fe plus 2 and some of them are exist at Fe plus 3. Now assuming suppose Fe plus 2 X atom. Total atom 98, automatically Fe plus 3 90 minus X. Now calculating charge. Here plus 2 charge, total numbers of atom X. That means automatically charge is 2x. Here charge is 398 minus x plus 3 charge. Now total positive charge. That means Fe plus 2 plus Fe plus 3. Total positive charge. So total positive charge equal to 2x plus 398 minus x. Now oxygen having negative charge. So total negative charge. Total negative charge. One oxygen having minus 2 charge. 100 atom is there. So 2 into 100. That means 200. Total negative charge is 200. Compound is neutral. So always total positive charge is equal to total negative charge. That means 2x plus 3 98 minus x equal to 200. That means simplifying 2x plus multiply, then it will be 294 minus 3x equal to 2. When we simplify, we get x equal to 94. X equal to 94, that means Fe plus 2 i's are 94 and remaining 4 are as Fe plus 3. That means percentage Fe plus 2 equal. So numbers of Fe plus 2 x equal to 94. That means 94. Total Fe atoms are 98. That means 98 into 100. That means percentage of Fe plus 2 simplifying approximately 96%. Similarly, percentage of Fe plus 3, that means 4 divided by 98 into 100, that means 4%. We can calculate percentage of Fe plus 2 and Fe plus 3 like this.